Hey guys, me again. You're going to get sick of my voice, aren't you? If you're watching this far ahead, well done. You've watched all the other videos. Nearly done with periodic table. This is the last video on the periodic table. We talked last video about generally how the electron configurations matched up beautifully with Mendelev's sort of pattern that he made, and that electron configurations and the valence electrons of each atom tell us something about their chemical reactivity, right? Now what we're going to do is just briefly, a couple of minutes, go through each of the major groups, I suppose, of the periodic table that you sort of need to know about. And the groups being, like we just talked about, the vertical groups. And so we're going to start with the alkyl metals. They're the ones that make sodium, that's where sodium is. They're the ones that explode in water. And they're all the ones that have one valence electron in their outermost shell. Okay? As we go down the group, it just means they've got an extra layer, that they're going to have another extra shell. But in each of those shells, that outer shell, they have one valence electron. So we're going to do this pretty quickly. So here is the group: lithium, sodium, potassium, rubidium, cesium, and francium. I'm going to jump back this side. And there's their electron configurations. You should be able to write those from previous videos in the PowerPoint. Remember, the electron highlighted in red is their valence electron. That's the one in the outermost shell. That's the one we care about for the reactivity. That's the thing that they all have in common, because there's nothing else they have in common. Their masses are different, proton numbers are different, everything else is different, but they have that in common, that outer valence electron there's only one of them. That's their original electron configuration. That's when they're unstable. That's when I've got the lump of sodium in my hand ready to throw in the water and it's unstable. It's there, it exists, but they exist as, in this case, 2, 8, 1. They've got all of those atoms in the lump of sodium have their little one valence electron in their outer shell. Now, something that we haven't talked about before is, can atoms lose electrons or gain electrons? Can we transfer them? And the answer is yes. Just like if you know, treat this as my valence electron. Here I am, I'm sodium. I've got other electrons that are in lower shells down, but I've got this one little valence electron here that's way, way out, right? My nucleus is where my chest is. I've got that one valence electron up here. I hope you can see that on the video. I can get rid of that if I want, all right? Or I can gain electrons as well. Now remember, all atoms seem to want to be like if you haven't watched the videos before, but they seem to want to be like the noble gases, the guys on the right of the periodic table, the ones that have full outer shells, that have 8 in their outermost shell. They seem to want to be like those. That's where they're most stable. That's their happy place. These guys don't have that, right? Their outer shell is not full. They've got one extra electron there. Sodium is the one we're talking about. So what can they do to be happy, to be stable? If they want to have a full outer shell just like a noble gas, what can they do? What can happen to this valence electron, the ones in red on your PowerPoint? Well, there's 2 options really. Sodium could, to fill its outer shell, that third shell, it needs to get 8 electrons. So it could gain 7. It could grab 7 from anyone who will give it to him. Right? Go around looking for people. Some of you might do that tuck shop at lunchtime. Can I have a 50 cent, can I have some money? Can I collect something? Can I collect another 7 electrons to have a full outer shell? Then I'd be happy. All right? That takes a lot of energy though for sodium, because there's a lot of electrons to collect. The easier option, and the second option, is that he can lose that one electron. He goes, you know what, I'm not really keen on this electron, I don't need it, I'm not holding onto it very tightly, it's quite loosely held, it's unstable, I can get rid of it. Once I get rid of it, that guy no longer exists. His new electron configuration is 2, 8. The 1 is gone. Look at his outer shell now, his third shell's disappeared and he's only got that second shell, and that second shell's now full. He's actually got an electron configuration that is now like neon, the noble gas next door to him in the periodic table. He's stable now. All right, that's pretty cool. All right, he's now stable. He's not neon. All right, he's still sodium because he's still got the same number of protons. The proton number hasn't changed. He's just lost an electron. So now that he's got one less electron, he's now stable. So when you see that, we see the video of the sodium going in the water, what we actually seen at an atomic level down there is sodium giving away electrons to all the water molecules, and the water molecules are grabbing electrons from sodium. And long story short, that makes some hydrogen gas, and that hydrogen gas, with a bit of heat, does some exploding. But really the explosion comes because sodium and all of the alkyl metals are really reactive, because whenever given the chance, they will take their one valence electron that they have at the start when they're neutral and get rid of it. All right, that's what they do, right? And they're easy to take those electrons from. That's why they're so reactive. So that's like the answer to our question, which is kind of cool. So that slideshow there, have a look at it. I'm not going to talk too much more. There are some reactions there that it does. So I don't think you can see this on the video, but when sodium reacts with water, we actually there's a chemical reaction that goes on, electrons get transferred, some bonds get broken between the water, so the water molecule's got some bonds, some atoms that stick together, they get ripped apart, sort of like Lego getting ripped apart. We make this beautiful, my boy, right, he loves making Lego. He makes this, or actually my little girl does too, and she makes this beautiful princess castle, right? Makes it up beautiful. It's a nice structure. We've got all the bricks that are connected together. We've got all our atoms, all right, connected together in this beautiful shape. My boy will come along to my girl's princess sort of castle that she's made and rip them apart, right? That's what's going on when you throw sodium in water. We're getting bonds ripped apart, electrons are getting thrown, sodium's giving up his valence electrons, and we rearrange the atoms. We put into something, a new shape, a new set of molecules. And the new molecules, we go from sodium atoms and water molecules to what we call sodium hydroxide, NaOH, and hydrogen gas, H2. It's a rearrangement of atoms. We break it apart, putting some stuff together. We'll look at future lessons will be about that, so you don't need to worry about those. They're called chemical reactions, and we can write them into chemical equations, which you've probably seen before. So all of these alkali metals will react with water to make the hydroxide, so sodium hydroxide, or lithium hydroxide, or potassium hydroxide, or rubidium hydroxide, etc. And hydrogen gas. They all do the same reaction. That's why Mendeleev put them in the same group. And they all do that because they have one valence electron to get rid of if they get a chance. That's the alkali metals. We're going to jump through the others pretty quickly because it's all fairly similar. There's a video there that you can watch. All of the alkali metals exploding in water. Kind of cool. Alright, the next group is called the alkaline earth metals. That's group 2. That's these guys. Alright, next to the alkali metals. Now, how many valence electrons? I'm hoping this PowerPoint's going to work. There we are. How many valence electrons do these guys have? Well, they're in group 2. So if they're in group 2, they must have 2 valence electrons, 2 electrons in the outermost shell. That's why they react the same way as they do. I'm going to jump back over here. And so when you put these guys, beryllium, magnesium, calcium, strontium, if you put them into the same situation, they will react the same way because they've got 2 valence electrons. Now remember, they want to be like the rock stars. They want to be like the noble gases. They want to have full outer shells. They don't have full outer shells. They've only got 2 in there. They can fit 8. They only got 2. 2 options. They can get rid of their 2 electrons, give them away, or they can take 6 and collect and have a full outer shell. What are they going to do? Well, these guys are metals. Metals always give their electrons away because there's only 2 of them to give away. So it's like they have 2 valence electrons this time. So I'm magnesium. If you put me into a place where some other atom's going to take these 2, I will happily give them up. And when I give them up, I now have a full outer shell. I get rid of my 2 outer shell electrons, the 2 valence ones, and now I have the inner shell, which becomes my outer shell. If you can follow that logic, replay it a few times. And my outer shell now has 8 electrons, just like before, just like neon. Alright, so I've actually become like neon again. I'm happy, I'm in my safe space, I've got a full outer shell. Lost 2 electrons. And all of these guys do that. And there's all their electron configurations. They also therefore react the same way, right? So if I was in a lab right now and I'll try to do this, we grab some magnesium metal, and he's Mg, he's got 2 valence electrons. I grab some magnesium metal, I throw him into a flame in a Bunsen burner, mate, goes off. Bright light, like the picture in here, beautiful bright light, reacts and makes magnesium oxide. The oxygen in the air and the magnesium metal get together, and the oxygen actually rips the electrons, the 2 valence electrons, away from magnesium. And so oxygen gets 2, which is actually pretty good for him because that gives him a full outer shell. Magnesium loses 2, that gives him a full outer shell. They sort of do a transfer, and they're all happy, and they make magnesium oxide. All of those metals do the same thing. So calcium does the same thing, calcium oxide, or beryllium oxide, etc. The slides are there with the reaction. They also react with acids, and they make salt and hydrogen gas when you put them in with acids, like hydrochloric acid or sulfuric acid. They make those as well. They all react the same way because, why? They have 2 valence electrons. Alright, we're going to skip over a few groups now. We're going to skip over the transition metals and these other groups. We're going to focus on group 7 or 17. We're only doing 2 more groups. These guys are called the halogens. These guys are cool, these are funky, these are all the gases. There are lots of gases at room temperature. They're very poisonous, a lot of them. And they all have, they're in group 7, so that means that they've got 7 valence electrons, right? 7 in their outermost shell. They are trying to achieve a full outer shell as well. They're trying to be stable. That's where they're most stable. They are not there. They are 1 short. So that if I had 7 pens, 1, 2, 3, 4, 5, 6, bear with me, 7. I have 7 pens. I have 7 valence electrons. I'm fluorine. I've got 2 more hidden down in my bottom shell, but I've got 7 here. I need 1 more to be stable. I need 1 more to have a full outer shell, and that's what makes me stable and unreactive, like the noble gases. I can either lose 7 or I can gain 1 more. Right? Now these are non-metals. We're on the non-metal side of the periodic table now. Okay? The left side is the metals. Metals, you know what metals are. We'll talk more about them later. And then on the right side, they're called the non-metals. It's actually worth, for a second, going back. So this little patch here, see the green sort of jagged line there? That little patch, that corner is the non-metals. They're not metals. Everything else are metals. There's a lot of metals in the world. We're now in the non-metal phase. These are the non-metals. And the non-metals will always, because they're so close to having a full outer shell, they've got 7, they just need 1 more. They're actually the ones that are going to go around and take them. Right? They're like the bully at school that, you know, when I was a kid I was a little bit weedy, right? And I had my lunch, and the bullies would come along and, you know, and take my lunch from me and I couldn't do anything about it, right? These are the bullies. These are the guys who goes, I got 7, where's my 8th electron coming from? I'm just going to jump over here. I got my 8th electron, I ripped it off sodium, right? Sodium wanted to get rid of it, so that's going to come later. Sodium gave up an electron to me. I found sodium, I grabbed him. I now have 8 electrons, I'm happy, I'm stable. But I got stable by taking electrons, sodium got stable, the metals get stable by giving them away. So now, after I've gained an electron, I become a stable non-metal with an electron configuration, again, like the noble gases. So every one of these reactions, every one of these groups are reacting, are trading electrons, either taking them or giving them to become like a noble gas, because that is where they're most stable. That's why the world works. A lot of the things that it does is this going on. Really cool. So they all react the same way. They're very reactive because they only need one. So they're like the alkyl metals, but the other side, they're very reactive. They're very good at taking electrons. Fluorine is absolutely the best at it. All right, chlorine not so good, and as they get down, they actually get worse at it. Fluorine is the best. He's the big unit, right? Halogens are also generally gases, so they're normally gases at room temperature. All right, chlorine, for example, chlorine is poisonous. It's a green poisonous gas. They always exist with another chlorine atom, so they make chlorine gas is Cl atom bonded to a Cl atom, so Cl2, chlorine gas. And all of these halogens do that. Fluorine gas is F2. Bromine is Br2, iodine is I2. They're diatomic, 2 atoms bonded together. Diatomic gas molecules. Chlorine's poisonous, all right? Will kill you. Remember that. Don't ever breathe chlorine gas in. But here's a cool thing. Chlorine gas is poisonous, all right? It's a halogen. He needs electrons to fill his shell. He will react with sodium metal who wants to give them up, right? We talked about that before. Sodium metal wants to give up electrons, super reactive. Also deadly. If you eat sodium metal, you're probably going to die, right? You've got a lot of water inside your stomach. It's going to react. It's not going to be good. Sodium metal, toxic, right? If you take it in. Chlorine gas, toxic. Sodium metal, reactive because it needs to give away its electron to be stable. Chlorine gas, reactive because it needs to grab electrons. They transfer electrons to each other. Sodium gives one to chlorine. Chlorine takes it. And it makes, what does it make? Sodium and chlorine come together to make sodium chloride. What's that? It's table salt, right? You put it on your steaks at home, right? When mum or dad burns it a bit much, you need a bit of flavour. Salt, it adds flavour to your food. And it's not toxic at all. How cool is that? Toxic, deadly, toxic, deadly, put them together, let them react, let them transfer their electrons. Now they're stable, and you can eat them all day. Well, not all day, don't go and drink salt, but it's not going to kill you. Pretty cool. All right, so that's the halogens. They react to form salts. That's their bottom line. They form lots of salts. The last group we're going to talk about is the noble gases, and we've already covered these fairly substantially, but they are super unreactive. All right, I'm going to go back in the slides for a second. They're super unreactive. Why? Well, they've all got their full outer shells. Their shells are full. And it appears like that's what's stable. That's what makes these atoms stop reacting. They're like, I don't want to give away any electrons. I don't want to take any electrons. I'm done. I'm happy. I'm in my bed. I've got my Netflix on. I'm chilled. Don't come and talk to me. All right, that's the noble gases. They're stable. therefore they don't react. It's very, very hard to make them react. We can force them. Like your mum and dad probably can force you to get out of bed, stop watching Netflix, but sometimes it's hard, right? We can force it, but naturally it won't happen. So they're very unreactive. The coolest thing that noble gases do is, like I said before, like all your neon tubes or all your tubes, your discharge tubes, they glow different colours when you light them up. You zap them with some electricity, they light different colours. Pretty cool. If we're in the lab, we've got some tubes we could show you, but this is sort of what they look like. A lot of funky stuff you can do with them, particularly in Year 11 chemistry. There's a lot of cool stuff we can study with those neon tubes or those discharge tubes. So they're really cool. I think that's it. I'm going to summarise and we're done. All right, so I've written a summary here, just really quickly. So atoms react when possible. So essentially what we've said is that an atom, let's do a whole summary here. An atom is made up of a nucleus with protons and neutrons. The protons give the atom its identity. The neutrons change its stability but doesn't change the identity. And electrons exist around the outside in shells. And the first shell can hold 2, the next shell can hold 8, the next one can hold 18. That's about all we need to worry about in Year 10. And we've now worked out that the electron configuration, the outer shell, is really important. It tells us all about how the atom will react. We know that the metals are on the left side of the periodic table. They have not very many valence electrons, 1 or 2 or whatever. And so they're likely to give away their electrons and react. And that's why they have the properties that they do. And so we know group 1 is called the alkyl metals, group 2 is called the alkaline earth metals. We jump across the transition metals in the middle, we jump across to the non-metals. Group 7 is the halogens. They have 7 valence electrons. They take an electron to become stable. And then we've got the noble gases who are already happy, they're already stable, they've got full valence shells, and they're all good. We learned that the periodic table was made by a guy called Mendeleev, and that he put it into rows, which are like periods, based on the mass, and then the vertical groups based on the properties, and we've now learned why they have the properties they do, because they all have, in a group, they all have the same number of valence electrons. We've also, we can write electron configurations now, and we're ready to move on to what happens, how do we look at these things as they bond, chemical reactions, equations, the language of chemistry. That's what we need to do next. All right, so thank you for listening. Hopefully this has helped. Hope everything's going well at home. If we're back in the classroom right now, because I've recorded this early, well, awesome, we're back. Love it, guys. See you later.